Good morning, class. This is Dr. Araipo, and we are looking at Chapter 3 Derivatives, Section 3.8 Differentials and Linear Approximation. First, differentiation formulas. We come across it often, as you've seen it. I put them up for you, so you'll be very comfortable with that as we go through the course, since the reverse process, anti-differentiation or integration is coming up. Logarithmic properties from the general case to specific cases such as natural logs and common logs, all of them are here. We should be comfortable with that. And now the concept of differentials. The definition for y equals f of x, we define dx called the differential of x by dx equals delta x. In other words, the run. If you look at this graph, y or f of x, if you pick up 2 points, the distance along the x-axis is called the run, delta x, or dx, or h. dy called the differential of y by dy equals f prime of x dx. We can replace delta y by dy for a function f, which is a continuous and differentiable function with a small dx if delta y is difficult to evaluate. So let me just give you some formulas and then we discuss the concept. Number one, f prime of x or dy dx, if we treat this as a fraction, the cross product gives us this. dy is precisely f prime of x dx. This is by formula. Delta y is f of x plus delta x minus f of x. Delta y is the change along the curve, the rise along the curve, which is the distance BC. This distance, BC. And it is the difference between this distance, f of x plus delta x, and this distance, which is f of x. So this is precise. Whereas dy equals AB. Is the rise along the tangent line. And dy is precisely f prime of x dx. So we can replace delta y by dy as long as delta x is small. The smaller the delta x, the closer the two values. Take a look, dy and delta y are completely different. But the smaller this value, the closer those are. So this is the precise definition of a delta y. If we move the minus 5x, it results in the second equation. Delta y can be approximated by dy, which is f prime of x dx, and the formula changes to f of x plus delta x is approximated. This is equal, this is approximated by f of x plus dy. The other thing is the linearization, which is finding the equation of a tangent line. So first, y minus y1 equals m times x minus x of 1. We've seen it, nothing brand new. If you move this one, it becomes this equation. M, we call it f prime of a, x sub 1a, y sub 1 f of a, and instead of y, we call it L of x. So the moment you see linearization, it simply refers to finding the tangent line. Nothing brand new, things we've seen before. So here's an example. We want to find dy and delta y. To find dy, you have to go with f prime of x first. So let's find f prime of x, because dy is f prime of x times dx. So f prime of x clearly is 12x squared minus 3. And dy becomes the same thing, tag along dx. Evaluated when x is 3, and delta x over dx is 0.2. This is elementary algebra. When you do the math, obviously, this is 9. 108 minus 3 is 105 times 0.2 gives you 20. To find delta y, we want f of x plus delta x, that means f of 3.2 minus f of x, that means f of 3. So first understanding this concept, then it becomes elementary algebra. Replace the x with 3.2, evaluate it. Replace it with 3, evaluate it, find the difference. I'm assuming everybody has an easy time with this calculation. So plug in 3.2, then plug in 3 and find the answer. Delta y versus dy. They are close, maybe not close enough, because take a look at delta x. The value of delta x in a matter of comparison to x is fairly large. The smaller this number compared to x, the better this approximation. Could somebody read this question, please?
The radius of a blood vessel is 1.4 millimeters. A drug causes the radius to change to 1.3 millimeters. Use differentials to find the approximate change in the area of a cross-section of the vessel.
Perfect, thank you so much. So we have the radius, or a drug causes it to change to 1.3, it shrinks, it goes down to 1.3. So their difference, which is 0.1, is dr, but it is important. Does it get larger or smaller? Gets smaller, so it's negative. So the new one, 1.3 minus 1.4, is negative 0.1. I want to use the differential to find the approximation. We have to find a relationship between the area of a cross section in the circular form with the radius, which is obviously a equals pi r squared. So r is 1.4, dr is the new one minus the old one. Pay attention how you calculate this. And of course, it's a piece of information from geometry, and with the approximation, we want dA. In other words, here's the circle with some radius r. In this case, r is 1.4, and it's going to shrink to a new one with a different radius being 1.3. That's the concept. So first and foremost, let's differentiate this and find the ADR, or a prime of r, and then dA would be the same thing times dr. In other words, if we take a look at this one, f prime of x is dy dx. Now a prime of r is dA dr. dy is f prime of x dx. Just look at this line and compare it to this one, and you end up with this situation. dA, which is the differential, is a prime of r dr. So let's differentiate this with respect to r, which becomes pi times 2r, or simply put 2 pi r. And dA is the product of the same thing with dr, just tag along dr. And now replace the r, that's why you write the given, with 1.4, and dr with negative 0.1. You can leave it as pi. If you want to replace the pi, please do not replace it with 3.14. Use a calculator, which gives you 3.14159, and it continues indefinitely. That gives you a better approximation. And write with however many decimals you need. Notice A and dA must have the same units, millimeters squared. Now, what about exact? Anybody knows how we can find the exact difference? In other words, never mind using the differential. Let's go back to algebra and say, okay, what would be the exact change? How would you find the exact change as the blood vessel has a radius of 1.4 and it goes down to 1.3. What is the exact change in the area? Any ideas? So we have this radius and it shrinks to this radius. Therefore, all we have to do, calculate the area of the new one with the radius of 1.3. So pi r squared, replace it with 1.3, calculated, that's the area of the small one. Then replace it with 1.4, that's the area of the larger one. And this would be the difference between the two. And that's an exact answer. That's the difference between the two. By the way, I hope you realize it's pi r squared. That's why I factored out the pi, and I put pi times 1.3 squared minus 1.4 squared. In other words, I'm calculating the area of the smaller one, calculating the area of the larger one, and their difference is what I'm writing. And notice it's extremely close to this one. Could somebody read this question, please?
A bacterial colony has a population P of T equals 20T divided by 10 plus T squared in millions T hours after a nutrient is introduced. Use differentials to approximate the change from T equals 2 to T equals 2.4 hours.
Perfect. So we want to use the differential for approximation. So how the approximation works, we are right here again. We want dy. In this case, we're going to call it dp. Remember, in this case, x is the independent variable. So it's here t. And y, in this case, the dependent variable is p. So what is given? T is 2. We're going to go to 2.4. So their difference of a 0.4 is delta t. Remember, instead of delta x, we're going to call it delta t because t is the independent variable. And p of t is given. Okay, so we want to find p prime of t, which is dp dt, and go to dp in essence. So I want you to compare this to f of x and understand that t is the independent variable. Therefore, we're talking about delta t, and p instead of y or f of x. So instead of dy, we want dp. So take a look and compare. All right. Now this uses the quotient rule. F prime g minus g prime f over g squared. Imagine this is the f function, this is the g function. Therefore, we want to find that dp dt. The derivative of the top is 20 times the bottom, minus the bottom gives you 2t times the top over the bottom squared. So dp dt has this format, 20 times the bottom minus 2t times the top. Here's what we have. The numerator simplifies as follows. 200 plus 20t squared minus 40t squared. The two can combine. And now we call this simply dp by putting a dt next to it. So take a look at dp dt. This is dp dt. So what is dp? Just tag along a dt, and the name becomes dp, which is the differential we are looking for, and replace the t with 2 and delta t or dt with 0.4. Do the math. Now, of course, you plug it into a calculator, you do the math. This is 4 times 20, 80 subtracted from 200. This gives you 120, just as an example. And this is 10 plus 2 squared, which is 4, making it 14 squared, which is 196. Do the math. This is what you get. And I'm going to write this as, by the way, this is the reason you have 0.245 millions of bacteria. So 245,000. That's the meaning of 0.245 million. Now, if we wanted to come up with the exact answer, instead of dp, we are looking for delta p. So what is the change in p? Well, plug in f of x plus delta x, plug in p of t plus delta t. In other words, p of 2.4 calculated, p of 2 calculated, and their difference is the exact answer, which is elementary algebra. Plug in the two values, and that means 189,000 bacteria. Now, you may say, well, that there is a discrepancy here, and the answer is, of course, because take a look. This number, the value of dt compared to t is not that small. The smaller the number compared to t, the better the approximation. In this example, we want to use differentials to approximate 51 squared. First, I want to quickly remind you of what probably you remember from algebra, a plus b squared. Which is a squared plus 2ab plus b squared. So we can say 50 plus 1 squared, which is 50 squared, plus 2 times 50 times 1 plus 1 squared, which gives you 2,601. So you can pretty much do that in no time in your head. So you already know the exact answer, but how does the differential work? Well, you need to find two things, a function and a number. What function? When you read this, you know what function you're looking for. We are looking to square this number, 51 squared. So the function we want, f of x, is the squaring function. So f of x is x squared. Then you want to find a number which is the closest number to 51 you can easily square. And obviously that's 50, which gives you 50 squared equals 2,500. So first you want a function. And all you have to do, read the question, 51 squared, so x squared. Closest number to 51 is a 50, which creates delta x or dx of positive 1. And then you take it from there. Before we continue, I want to make sure everybody understands. With the choice of x equals 50, since we want to go to 51 squared, it is getting larger by dx or 1. If you were interested, and I'm going to leave it for you to do it at home, to calculate, let's say, 48 squared, I hope you realize in this case, your dx is -2. So you want to try this at home. In the meantime, here's the function, and we are going to use f of x plus delta x is f of x plus dy, where f of x is x squared, and to find dy first, we find f prime of x, which is 2x, and dy is 2x dx. So using this formula, f of x plus dy. So this is the approximation we're going to use. And we want f of 51 in essence. Remember, we want 51 squared. That means we want f of 51. That's the meaning of 51 squared, which means x is 50 and delta x or dx is 1. So replace the x with 50. Replace the x with 50, replace the dx with 1. This is obviously 2,500. This is 100 times 1. They add up to 2,600. And as I mentioned, the exact was 2,601. As you can see, they are extremely close, extremely close. Why is that? Because delta x compared to the choice of x is extremely small. when delta x is small compared to x, the two values are very close. So this approximation is an excellent approximation. You're done. But I want to show you the second method I discussed, known as linearization. If you want to use the linearization, that means you want to use the tangent line. That means you want to come up with the tangent line of this function. At what point? At x equals 50. In which case, you need the pair 50, comma 50 squared, which is 2500. And you really want to stick with this formula. Again, y minus y1 equals m times x minus x of 1. This one is just to follow the linearization formula. You don't have to. Just write this one, y minus 2500 equals m. Now, what is m? Remember, f prime is 2x, and you want to replace that with 50, which makes it 100. So f prime, is this the slope? No. That represents infinitely many slopes. If you replace the x with 50, makes it 100. So I'm going to write it at the top of it. So you see, that's the good old tangent line. Y minus 2500 is 100 times x minus x of 150. Or again, this is the way we also mentioned the L of x, if you will. So you finish the job again. F of 50 is the 2500. F prime of 50 is 2 times x or to 100. And when you multiply, you get 100x. And this is minus 5000 with 2500 gives you minus 2500. This is L or L of x. Now, if you want 51 squared, replace the x with 51, everybody. And that must be identical to what you got with the method of differentials. The method of differentials and linearization must give us exactly the same answer. Otherwise, we have made a mistake. And as I mentioned, try 48 at home. Here's the next question. We want to repeat the same concept. This time we want to take the square root of 27. And again, we need two things. We need a function, and we need a number closest to 27 that we can easily take a root of. Can you come up with a function and a number? What would that function be? Y equals f of x equals what? Anybody? Look at the action you're taking. Let's read it. Square root of 27. So square root of something. F of x is square root of x. What number can you take a square root easily, which is close to number 27? Closest number.
25.
25, and that is 5. So the number you are going to use, so you need a function, as I mentioned, and the number you're going to use is 25, which means from 25 to 27, delta x or dx is positive 2. So you need a function, you need a number, and you want to come up with delta x, and delta x is 27 minus 25. And just to make sure we understood this, so this is 27 minus 25. If the question was asking what is the square root of 24, then you do exactly the same thing, but your dx is negative 1. So be very careful, and the sign is important. Now we go through the process. F of x plus delta x is f of x plus dy, where dy is f prime of x dx. You have to differentiate this. This one is x to the power of 1/2. So 1/2 x to the power of negative 1/2. We've done it many, many times. I'm hoping by now you have no problem changing to x to the power of 1/2 and finding f prime, and of course tag along the dx, and that becomes dy. So here's your f of x plus delta x. Square root of x plus 1 over 2 square root of x dx. We want square root of 27, which means f of 27, which means f of 25 plus 2. That's what we are looking for. Which means replace the x with 25 and dx with 2. That's the meaning of it. So square root of 27, which is f of 27, is f of 25 plus 2. That means precisely what you need to do. Let's do that. Square root of 25 is 5. These two cancels out. These two, you have 5 plus 1/5, and you can rewrite it. 5 and 1/5, or 5.2. That's an approximation. It's pretty close. You can check it with a calculator. What I'd like you to do at home, I want you to find square root of 24. Also, I want you to find L of x, and then, which means finding L of x, the tangent line for this function. Find the tangent line for this function at x equals 25, comma, square root of that, which is 5. And for the slope, you don't have to do much. You've already come up with f prime of x. If you plug in x equals 25, you already have this slope. So it should be pretty easy. I'll leave it for you, and then evaluate the square root of 27 accordingly. They must be identical to 5.2. Here's the last question. Could somebody read that, please? Measurement error in a manufacturing process, ball bearing must be made with a radius of 0.6 millimeters, with a maximum error of positive or negative 0.15 millimeter. Use differentials to estimate the maximum error in the volume of the ball bearing. So the radius is 0.6, and the maximum error in that is plus minus 0.015. That means delta R or dr. And the relationship between a volume of a ball bearing and the radius, you have to know this is in the shape of a sphere. The volume is 4/3 pi r cubed. So this is the spherical shape. R is 0.6 millimeter, delta R is plus minus 0.015 millimeters. And again, we should know this from basic geometry, or we've seen it in algebra. And of course, we are interested in finding using the differential to estimate the maximum error in the volume. That means we want to find dV. So notice, if this is the radius, you want to add 0.015, make it larger, or you want to subtract, so it becomes either larger or smaller in a matter of comparison. And so you have this shape that changes accordingly. So as far as the estimate is concerned, let's find, so we want to find dV. Let's find the derivative of this guy with respect to R. dV dr, you can even say V prime of R, is 4/3 pi is just a number, is a coefficient. So you want to differentiate R cubed, which gives you 3R squared. We've seen this before. And this is 4 pi R squared. So that's dV dr. Now, what is dV? The same thing, tag along, dr. Now, what is R? 0.6. What is dr? Plus minus 0.015. So you just do the math, plug it into a calculator at this point, class. 4 pi, replace the r, replace the dr, and you get dv, which is this much. And again, if you want to replace the pi, please don't replace it with 3.14 because that's an approximation. Change it to what the calculator gives you. So put it into a calculator, and with a bunch of decimals, however many they ask you, 0.0678584 or 0.0216 pi cubic millimeters. Notice the units of the volume and the units of dV, the change in volume, they must be identical, and they are. So this is the exact difference. If you were to, this is the approximation, my apologies. If you were to find the exact difference, then you would have to add and subtract this much from this. In other words, 0.6 plus 0.015, calculate the volume, and then subtract the volume with the radius r equals 0.6 from it. That's one extreme. The other extreme is that you subtract 0.015 from 0.6, calculate the volume, and subtract that one from when the radius is 0.6. You do get two different volumes, and that's why we have three different, cases. We have the original one. This one is the original one. Now this is when it gets smaller, and this one when it gets larger. And they do create different answers. But nevertheless, this is the maximum amount of error using the differentials.